Okay, so what we are talking about today are properties of solid structures, crystals. Okay. Now, if you can elucidate, if you can figure out the structure of a solid, it gives you a lot of power. And I think it's easiest to explain. So I've got this fancy thing up here just trying to illustrate that there's a lot of computing power that goes into this. But one thing those are vitamins, by the way. So if you take some of those vitamins, which kind of look like these 3D structures, or there's some that are even more complicated in there. These are all biomolecules, things that interact in your body, and they do something. Okay, and I should have the names up there for everyone. But the point is it's because of their structures, because of how they're made up, that gives them the chemical properties, that gives them the behavior in your body that they have. So this is really powerful stuff. And the drug companies, they work hard to figure out what the molecular shape is of this vitamin, for example. And if you just modify one OH group or move one structure, just change it a little bit, you know it's definitely going to do something in the body. Is it going to help solve the problem you're trying to help, or is it going to make it worse? If it makes it better, let's change it a little bit more. Let's change this. And drug development, there is big, big money in doing this sort of thing. The issue is, though, I think what's a real heartbreaker here are these things. In order to have the computers and do their job and get these three-dimensional structures where you know where everything is and you can deduce how they're behaving in the body, first you got to get a crystal of this stuff. And I was talking to a guy who actually did this type of work, and he says this is the real hard part, is getting a nice shaped crystal that you can use to get the X-ray diffraction. But so it's interesting, though, because it's really powerful. Big bucks, for sure, what they're doing. So all we're talking about are solids, and what are their shapes at the molecular? What type of crystals do they have? So you have graphite versus diamond. And both of these, Tegan, are made of the exact same element on the periodic table. What's that element? The graphite is what's inside your pencil lead, right? Just sloughs right off on the paper. Diamond, exact opposite. What element is it? Anybody know? Carbon. They're both made of carbon. They're just packed differently. Okay? If we look at diamond, its structure looks like this. It's kind of hard to tell that it's a tetrahedral shape, but there's a lot of interaction between those different carbon atoms. And there's a complicated structure in there. This thing is really solid and very, very hard. So it's that structure that gives it its properties that diamond has. Graphite. You take your pencil lead, and it's pretty easy to slide things along. Graphite is one of the, I don't know if there's any more. It's a solid lubricant. Usually lubricants are, liquidy, but the Cub Scouts, I remember that derby, those derbies. This is not politically correct, but it's ridiculous because who makes those things? Do the kids make them or their dads? Their dads make them. And then when you take that little car to the derby, little Johnny, you can't touch that car, right? Because he could bend the wheel, or he could, kids should go there and have fun. There should be, doing derbies and stuff. What a real derby, crashing, right? But no, man, it's all about the race and getting anyway. So anyway, graphite is the only lubricant you can use. That's the rules in that. But anyway, what I'm trying to get you to think about is you saw the structure for a diamond. Graphite is made of the exact same thing, carbon atoms, but has to have a different structure. Can you imagine a structure that's going to allow you to just slide it along and just sloughs off? right? Ooh, it's really easy. What kind of structure would give you that? Nature developed it over who knows how long, right? I mean, no, nature didn't develop this, just happened, didn't it? But if you could deduce it, it would really help you develop some lubricants. There it is. See if I can get it to pause here. Pause. Just layers of carbon. Now those individual layers might be kind of tough, but even there, I don't think so, because look at that. There's a gap here in between these. A big gap in between these layers. So you can see how just one layer just sloughs off after another. So it's really, really easy to write with. Okay. But these aren't gas molecules. Something has to be making these two stick. What's making it stick? What type of force? Starts with can't be hydrogen bonding. Has to be intermolecular forces. And which one? What does it consist of? It's all carbon atoms. Has to be which one? Has to be London. It's all carbon atoms. So you can't talk about dipoles. You can't talk about hydrogen bonding. Has to be just London. Which is great because that's super weak. It's going to make the lubricant even better. Okay? So on what?
I'm just saying because on here it says covalent network solid held together.
We'll get there. Okay. So there's all these different types of solids. Okay? And as we go up, the arrow's showing the stronger the interaction.
Stronger interaction or stronger intermolecular force? So
These aren't intermolecular forces. These are the forces that hold these solids together. So some of them might be intermolecular forces, but all I'm saying is right now we have this range of solids, and they're going to be made up different ways. And as we go up, the interaction's stronger. So you have these different solids and stronger interactions. They're going to have different melting points. Would the melting points also be getting higher, or would they be getting lower as you go up? They'd be getting higher, right? Because that's stronger interactions. They don't want to turn into a liquid. Good. So you'd say higher melting points. Okay, let's start at the top here. A covalent network solid held together by what? Ooh. She nailed it. What does covalent mean? Definitely, you got to have nonmetals. This is only going to work for nonmetals. Okay? What else does covalent mean? Like a covalent bond versus, the only other bond we've talked about is, there's an I, ionic. What's the difference between the two? Covalent shares electrons. It's kind of, I never liked this word share, and I can't think of a better one. But, right, you've got all these electrons everywhere. Nobody knows whose electrons are whose. It's just that what holds it together, everybody wants the electrons. So yeah, that's what's holding them together. You have electrons in between them too, and they're holding it together. But some want electrons more than others. So they're going to tug on it harder, so the electrons aren't going to be, you know, they have the whole orbital idea. So you got these weird funky shapes of orbitals. So they're not shared equally. Okay. So that's our covalent network solid. So if you have stuff like, this would be one. Diamond. All right.
So diamond is a covalent.
Diamond is a covalent network solid. C. Diamond. Okay. Ionic solids, held together by probably everybody? Ionic bonds. Okay. Now that is very different, right? You'll have a sodium ion, chloride anion. Well, yeah, plus and minus, they're going to stick together pretty well, right? Okay. Ionic bonds. Not as strong as diamond. Now, Dreeksa really likes these animations, so I got to...
Sodium chloride is typical of ionic solids. The crystal contains alternating sodium cations and chloride anions packed in a three-dimensional array. Ionic solids are brittle if deformed and will fracture along planes of packed ions.
Okay, so not really much to say there. I remember when I see this sort of thing, I remember a talk I went to, and this lady was getting her doctorate, and this is what her research was about. It was a much more complicated structure than sodium chloride, but it was the same idea. It was a solid, and it was this packing, and she did all these computer simulations and calculations on it, and the whole time, you know, she had showing pictures like these. And I'm just looking at it and thinking pretty much what I think everybody else is, and maybe what you are too. It just looks like a bunch of balls, right? And nature is going to pack them the way that it can, right? So, I mean, she showed picture after picture after picture, and all these big, heavy-duty calculations. And finally, at the end, they asked for questions, and someone asked, well, can't you just do the same thing by dumping a bunch of balls in a bucket? Oh, she did not like that question at all. But everybody was thinking it, right? But, oh, it wasn't good. I'm glad I didn't ask that question. Yeah.
What is the significance of the hammer?
Oh, the
Metal part?
brittle. You can't bend it.
Yeah,
It's just going to break
I was
on you.
just-
It's just going to break on you. Okay. So that's ionic. So ionic solid. You know what's an ionic solid if you see a compound and it has a what again?
What?
What do you have to see and say, oh, that's an ionic compound? That's not a molecule.
Oh,
Yeah, negative and positive, but
non-metal.
a non-metal and a metal. Always see a metal. For me, it's easier to see the metal because molecules just have, non-metals. Whenever you see a metal show up, it's got to be ionic solid, right? Well, metal with something else, plus and a minus. Okay. So ionic solids, sodium chloride, right? Iron 3 chloride, just all these ionic compounds. Wherever you see a metal. Okay. Okay. Let's jump down to metallic solid. Held together by, there's a little hint.
Someone said metals.
Held together by the electron
So,
C. Now, what the heck is this?
yeah, what is that?
Okay. Remember on one side of bonding, we have covalent bonding. And we have, this, like Gabby said, the sharing of electrons. And if you have something really electronegative, well, then electrons are going to hang out there more often. But the point is, there's still electrons in between them. But nobody knows whose electrons are whose. They're just, right, they're all there. Metallic solid, kind of the same thing, but it's just that they donate all these metallic atoms, like copper. You know copper is a solid. And every single, but copper, where's copper? Oh, remember copper's not a very good one. It might be easier to think of something like calcium. How many valence electrons does calcium have? 2. So all of these metals, they all want to give up electrons. They don't want to take them. Nonmetals, totally different story, right? Look at N and O and P and S. You count over to the nobles. Why does everything want 8 valence electrons? They're happy, very, very stable, right? So nonmetals, they all want the electrons. So that's what makes these covalent compounds work so well. There's electrons there, and they're not going to be sharing them equally, but they all want the electrons. Metals, they don't want them at all, right? Calcium wants to have what charge? calcium wants to have what charge?
-2.
Are all metals want positive charges? They all want this noble gas core notation, or a pseudo noble gas core notation. So calcium wants to lose 2 electrons so it can be like argon. So in this crystal, you've got calcium plus 2 everywhere. Where'd those 2 electrons go? They went into the sea, a cloud, right? But it's evenly distributed. It's evenly distributed because calcium plus 2, right? And calcium plus 2 in this crystal, they're everywhere. What's in between them, right? The electron C. The electrons. So you think calcium plus 2 and calcium plus 2 would push apart. No, you have these electrons all over the place. And it's evenly distributed. So that's why I kind of think of a C as, you think of C, it's not higher at one end than it is at the other. It's just the same everywhere. Versus a covalent compound, right? There, that C is totally oddball. It might be this height here, then a much higher over here where fluorine is, because fluorine wants the water, fluorine wants the C. Make sense? So it's kind of an oddball C with covalent compounds. But anyway, metallic solids held together by this electron C model. Here's another animation.
Bonding in metals is described by the electron C model. Solid metals behave as if constructed of a repeating pattern of metallic cations, surrounded by delocalized electrons. These electrons are free to move among the many cations in the crystal. This model explains the relatively high electrical and thermal conductivity of metals. When deformed, no bonds are actually broken. Instead, cation planes slip past one another, leading to the metallic properties of ductility and malleability.
Right? If that didn't happen, copper wouldn't bend, copper would snap. So you're not breaking any bonds, you're just moving stuff around. Okay? It's almost like a solid liquid, kind of in a weird way. Okay. So name any metallic compound, copper, iron. Notice how all this is just the formula. Iron solid. Where if I would have wrote FeO solid, no longer is that a metallic solid. That's now a what? Which one? Ionic solid. That would fall under this category, whereas iron solid falls under this one. So pretty much just look at the chemical formula to see which category things fall into. There's one left, molecular solid. Okay. Give me a name of a molecule, Jerixa. Give me a name of any molecule. What's that? Name of a molecule. Na's definitely not a molecule. You just gave me a metal. So again, but hang on. This is good practice. No way, because you just named a metal again.
Okay, so what is it? F and Cl? Is it both?
F and what? Cl. Works. I don't know if it actually exists. You'd have to draw the Lewis dot structure and all that stuff. But that's the idea, right? I played, I think you've seen me play with liquid nitrogen, right?
Oh, okay.
Molecule. And if I made liquid nitrogen even colder, right now it's negative 330 degrees below 0 Fahrenheit. But if I made it even colder, I could turn liquid nitrogen into a solid. Would nitrogen be a molecular solid? Now it can't be either of these because it's not a metal. So it has to be either this one or this one.
That's solid, it's a covalent.
Which one would it be? It's a solid, so it has to either fall into the molecular solid category or the covalent networks category. Right? It has to, because it's a non-metal. Which one would it be? All you do is you
said the strongest interaction.
hang on. All you do is you look at the formula and you see, is this a molecule? You bet it's a molecule. It's N2. right? So it's a molecule, 2 nitrogens flying around. So this is a molecule. So this has to be molecular solid. The weakest of the weak, right? Because if you warm it up a little bit, man, it turns into a liquid. So this is extremely weak. What holds together molecular solids? Ooh, very good. London, all those intermolecular forces, you name them. I just say intermolecular forces. But you're right, Miss Munoz, because there's 2 crystals, right? You're right. This case would be London because it's N2. Okay, but all molecular solids are held together by intermolecular forces. Mm-hmm.
So they're all solids, correct? But the lowest of the lowest are the molecular ones?
Yeah, molecular solids are going to have the lowest melting point. They're going to melt the easiest because they're held together the weakest. Held together the strongest are the covalent network solids. Okay. So, for example, if you did something like, well, I don't know, just jump to this one. There's a lot of homework questions like this. They say, which of the following do you expect to be molecular solids? Which ones would you say are molecular solids? Ooh, good, chlorine. That's definitely a molecule. I agree with that one. What would be another one? Or are there any more? It has to be a molecule. What's that? CD. But it's not. One thing that I think you have to get used to with these types of questions, whenever you have any element all by itself, it can't be a molecule. It's all by itself. So don't look at cadmium. So not that one. Are there any others that are molecular? There's one more. Lithium is a metal. So this is going to be ionic.
Oh, what was your question? Sorry.
There's only one left. A. What type of solid would cadmium be? Cadmium is it's a transition metal. It's a metal, so it would fall under metallic. That'd be metallic. So that's a game you're going to be playing. And we'll come back and do a few more of those, right? We'll come back and do a few more of those. But let's take a look first at this type of, this is the hardest question you're going to be thrown at. And I don't think there's very many of them, but this is the toughest. Here's, in the cubic way of packing things, there's 3 ways. You can have the atom at each of the 8 corners of the cube. That's simple cubic. You can have it body center cubic, so then you've got at each corner of the cube you have a part of an atom. Then in the middle you have one. And then face center cubic, again you have all the corners covered with part of an atom. And then at each face you have half an atom stuck in the lattice. So what these are is, this is how some of the cubic crystals are formed. This is the exact same lattice again, again, and again, and again in space, everywhere. So that would make it a crystal of that type of lattice. So what we need to know to get our homework done is, what are the number of atoms in each lattice? Okay, simple cubic. We have there's 1/8 of an atom at the corner of all of these. And how many corners does a cube have? Has 8. So that means there's 1 atom just by having the corners. So simple cubic just has 1 atom. That's it. because it has 8 corners, 1/8 at each corner, all it contains is 1 atom. The body-centered cubic, he's got those 8 corners plus 1 in the middle. So you would have 2.
And there's only these 3 structures.
That's all we're going to worry about. And then there's face-centered cubic. He's got the 8 corners, and then a half here, half here, half here, half here, right? All those at the face have just a half stuck in the lattice.
8 halves? 4?
So you count 4. I count, well, the corners give you 1, right? The corners give you 1, and then these 2 sides, well, here, those 2, there's another one, that's 2, that's 3, and that'd be 4 total. So there's 4 atoms. Okay, know this. Otherwise, you can't answer this question. Okay, here's an example of one that you're going to have to worry about in the homework. Gold has cubic crystals. That means that gold actually looks like one of these structures. And our problem is to figure out which one. So he has a unit cell. It has an edge of length 407.9 picometers. So you've got the cube. And that edge length is 407.9 picometers. The density of the metal is 19.3 grams per cubic centimeter. Okay. From these data and the atomic mass, calculate the number of gold atoms in a unit cell, assuming all atoms are at lattice points, which they are. What type of cubic lattice does gold have? So we have to figure out how many gold atoms are in here. What's the number of gold atoms in there? And you know the answer has to be one of these. If the answer is 2, then we'll say it's body-centered cubic, and so on. Okay.
What is this, number 8?
Good. We're going to find the volume of the cube. Now, because you can find the mass of the gold if you just multiply it by the volume that you use, right? You just multiply it by this. Multiply it by the density. And we can get the mass of the gold. So all we're going to do is figure out the volume of this extremely small guy.
Is A gold?
Yeah, A is gold.
Oh, A.
We're going to find the volume. And then we'll multiply that volume over here. And then we'll get the mass of the gold. The mass of the AU in the cell. So this has to be the mass of either 1, 2, or 4 gold atoms. But looking at that, you can't tell, right? It's the mass of 1, 2, or 4 gold atoms. You're not a computer. So what you're going to have to do is figure out what the mass is of one gold cell, figure out what the mass is of one gold atom, and divide that into this. And then we'll either get 1, 2, or 4. Right? So then we'll take this number, put it on top, divide it by the mass of one gold atom, and we'll get 1, 2, or 4. If you don't, you screwed up.
So multiply 407.9 to the 6th power will give you the area.
Okay, let's figure that out. Okay, but you see the big, maybe you don't see how to do the individual steps, but you see the big picture? Okay, so let's do the first part. Let's figure out the volume, what Crystal's talking about here. So we're going to take 19.3 grams per cubic centimeter times the volume. Now, how do you get the volume of any cube? Multiply what by what by what? Length by width by height, right? Length by width by height. Aren't they all the same? Yeah. So we'll just cube it, but we're in the wrong units. We're in pico. And you pretty much have to Google it. But if you Google it, you'll see 407.9 picometers. A pico is 10 to the negative 12. Pico is 10 to the negative 12. But if we want to multiply, get the volume, we don't want it in cubic meters. We want it in cubic centimeters. Otherwise, it's not going to cancel. So let's convert this into centimeters. Okay. In a meter, how many centimeters are there? 100. 100 cents in a dollar. So that's really 10 to the second. You can really just add exponents if you're good at this. If not, just do it on your calculator. But you'll end up with 10 to the second, and 10 to the negative 12 is just going to be 10 to the negative 10. But we'll end up with 407.9 times 10 to the negative 10 centimeters. So that's what we have to cube. 407.9 times 10 to the negative 10 centimeters. You have to cube it, and then multiply it by 19.3. So what I'm going to do, 19.3 times. And you notice you do have a cube button. It's kind of orange, so we're going to have to use the shift to get there. So I plugged in the 19.3. Now the 407.9 EXP for the 10 part. EXP, that's times 10 to the 10 plus minus, hit the button. So I've got 407.9 with a little negative 10 up there in the corner. Now I have to cube it. So I'm going to push shift first and then my X cube button. And then I'll have it cubed. So that's what the answer is, cubed, but I have to hit equals because I multiplied it by 19.3. So I end up with 1.31 times 10 to the negative 21. You can always just keep hitting equals, and if it doesn't change, you're done. But 1.31 times 10 to the negative 21 grams. Okay. So what is the mass of one gold atom? How do we get that again? We use, okay, gold is 196.97 or so. How do we get the mass of one gold atom, though? Do we divide or multiply by Avogadro's number? Divide, because this is the mass of Avogadro's number of atoms. So to get the mass of 1, divide it by Avogadro. 6.022 times 10 to the 23rd. Okay. 196.97 divided by 6.022 to 10 to the 23rd. 3.27 times 10 to the negative 22 grams. That's the mass of one gold atom. Okay, so now we're ready to find our total mass. Divided by one gold atom. That's going to be 1.31 times 10 to the negative 21 divided by 3.27 times 10 to the negative 22. And if I didn't get 1, 2, or 4, we got to start all over. That would not be good. Plug it in. It worked. Anybody get it? Got 4. There's 4 gold atoms in each lattice. So that means, so that's the answer to the first part. So what type of cubic lattice does it have? Yeah, face-centered. Sorry. There's 4 atoms. So it's face-centered. Okay. So hopefully there won't be too many.
Like we just have to find the cubic lattice.
So what they are always going to, all of them are set up the same way. They're going to give you the length of one side. So you have to cube it, but get it in the right units. It's always going to be in centimeters, right? So get it into centimeters, multiply it by your density, and then you get the mass. So divide that then by the mass of one atom of the stuff. And it always works. You always get 1, 2, or 4. Is it okay? Let's try some of these. This is where the majority of your homework, though, I think, is this kind of stuff. But classify each of the following solid elements. So these are solids, and they either have to be molecular, metallic, ionic, or covalent network solids. Tin. Vivian, what would you say tin is? A metallic sounded good to me because it's a metal, right? Isn't tin a metal? Oh, it's getting close to that. Someone's got to climb up there and draw in the stairs, right? But tin's a metal, so your first guess was right. Man, we really need the stairs for germanium. You really need the stairs for germanium.
It's metal.
No, it's not. So it's not a metal. It's a metalloid. So knowing that,
I thought they would just elevate you what's supposed to
what would you classify germanium solid as? It can't be metallic because it's not a metal. So it can't be ionic. So definitely it's not those two. Your only real choices here for this guy, it's not a metal. So it has to be either molecular or covalent network. I can't write network. And it's definitely covalent network Y. Because it's not a molecule sitting there all by itself. That's the only reason. Good. How about sulfur? S8. Ooh, good. Someone said it. What'd they say? Ooh, I heard 2 now. Molecular or covalent? This is does it consist of all nonmetals? It's the same thing, but yeah, it's all nonmetals. So it has to be a molecule. So it has to be molecular. It has to be molecular. How about iodine? Solid. Molecular again. Let's jump down here. Oh, here's a good one. You can do this, you can handle what the homework throws at you. Besides the calculation one. Arrange the following compounds in order of increasing melting point. So what I would do is I would figure out what type of solid each of these is, and maybe write it down next to it or something. And then that'll allow you to list them out from weakest to strongest, right? From lowest to highest melting point.
The first one is covalent one?
For A?
I mean, what's it called, that bond, that non-metal plus metal, ionic bond?
Ionic. Good. This one's definitely going to be ionic because you see calcium. Crystal Zamora, what would you classify B as?
So on that one,
What type of solid? Right? Your only choices are these guys. Those four. All right.
I believe it's covalent.
We had ionic, covalent network. We had metallic, and we had molecular. Anybody give her a hand?
Alright. Is 8 diphenol?
Now, just don't worry about. Just what category would it fall into? Now, this is where I think it's confusing. You should be looking at.
Covalent over molecular.
Definitely, you're doing it right. You're thinking right if you're looking at these two. And the trick to doing this is covalent network. It's covalent bonds within the molecule, but they're talking about molecules sticking to molecules. So it's molecular. The only time it's covalent network is when it's one atom sitting there all by itself, like diamond. C, diamond. That's it. That's the only one where it's covalent network. Or germanium, just sitting there. That's the only time it's covalent network.
So that guy's
So this guy is going to be molecular solid. How about C?
oh, well, they're sitting by themselves, right? That last.
How about C? Crystal Munoz. How about C? Molecular again. Yeah, it's a molecule.
Just spaced it.
And then how about D? Jasmine. Ionic. Good. Okay. So this is how it starts for me. Now I list them from lowest to highest melting point. Molecular first. Good. So which one would you list first then? B or C? Yeah. Whoa. I like B first, then C.
Why?
Why do I like B first, then C?
Because of the O.
Because of this. Oh, look how nice and free he is out here, right? He can do this. All these other molecules just like him can really fit in and suck up. Over here, he's kind of tied up. It'll be hydrogen bonding in both cases, but this one will have less hydrogen bonding than this one. Okay, so B should be weaker than C. So B should be weaker than C. Now you have to pick between two ionic solids.
But KCl is weaker because the Cl is closer to the no.
Well,
Right?
what charges are we talking about? K has a plus, Cl has a minus. What about calcium? Plus 2 and a. So which ones would be held together stronger? The plus 2 and minus 2. So list that one last. D and then A. Okay. So that's the game you're playing with the homework. So good luck. I'll be glad to help you out. Just come by.